109 containers lost. A chemical fire that burned for 5 days. The force that did it? It wasn't a hurricane. It wasn't a rogue wave. It was a math equation. This is the forensic breakdown of how a fully compliant modern container ship was defeated by physics, and why the regulations still haven't caught up. The system before it breaks. The ZIM Kingston was not some aging rust bucket. She was built in 2008 by Samsung Heavy Industries in South Korea, one of the most advanced shipyards on Earth. 260 meters long, 32 meters wide, 40,030 gross tons. She could carry 4,253 TEU, the equivalent of over 4,000 standard shipping containers. Her engine, a direct-drive diesel producing 36,560 kilowatts, turning a fixed-pitch propeller. She was equipped with everything the SOLAS convention required: Voyage data recorder, analog inclinometer, full navigation suite. On paper, this ship was exactly what modern shipping demanded: big, efficient, compliant. But compliance and safety are not the same thing. In October 2021, the ZIM Kingston was on a routine trans-Pacific run, carrying cargo from Asia to Canadian ports. Her holds and deck were loaded with 1,965 containers, 1,273 stacked on deck, 692 below. But buried in that manifest were 5 containers that would turn a shipping incident into an environmental nightmare. 4 40-foot containers, each holding 23,800 kilograms of potassium amalxanthate, an industrial chemical used in mining, and 1 20-foot container packed with 18,000 kilograms of thiourea dioxide. Potassium amalxanthate has a very specific property. When it contacts water, it decomposes into a cocktail of flammable and toxic gases. On a ship surrounded by ocean, that's not a risk factor. That's a time bomb. By mid-October, the ZIM Kingston reached the coast of British Columbia. Canadian ports were overwhelmed. A backlog of vessels stretched for days. The ZIM Kingston was told to wait at anchor near La Perouse Bank, off Vancouver Island, approximately 27 nautical miles south of Ucluelet. She sat there, loaded, exposed, waiting, and the weather was changing. The hidden defect nobody saw coming. On the night of October 21st, conditions deteriorated. Winds hit 42 knots from the southeast. Waves built to 5, then 6 meters, coming from the southwest. That mismatch matters. Wind from one direction, waves from another. The ship wasn't facing the swells head-on. She was exposed beam on, her broadside to the waves. And then the math equation the hook mentioned. This is where it starts. The ZIM Kingston began to roll. Not the normal, predictable roll of a ship in heavy seas. This was different. Each swing was bigger than the last. The ship tilted 36 degrees to port, then 36 degrees to starboard. Back and forth, accelerating. This phenomenon has a name: parametric rolling. You know it was a math equation that did this. Now let me show you exactly how that equation works, because this is the part that most ship captains have never seen explained. Every ship has a natural roll period, the time it takes to swing from one side to the other and back. It's determined by hull shape, weight distribution, and metacentric height. Parametric rolling occurs when the wave encounter period, the time between each wave passing under the ship, is approximately half the ship's natural roll period. When this ratio hits, the waves don't push the ship, they pump it. Think of pushing a child on a swing. You don't push randomly. You push at exactly the right moment, at the natural frequency. Small pushes build into massive swings. That's the equation. Simple ratio. Catastrophic result. Scale model tests, conducted later at a 1:50 ratio, proved that parametric rolling on this hull could begin in waves as low as 2.6 meters. The ZIM Kingston was sitting in 6-meter seas. She never had a chance. At the peak of the rolling, instruments recorded lateral accelerations of nearly 0.95 g at Bay 14, one of the forward cargo sections. That's almost the force of gravity, but sideways. Container lashing systems are engineered for a maximum of 0.6 g lateral force, 0.95 grams versus 0.6 grams design limit. The math was over before the first container moved. 109 containers went overboard. Some shattered on impact with the water. Others sank intact, becoming invisible hazards on the ocean floor. But the worst was yet to come. Among the containers damaged but not lost overboard was one carrying potassium amalxanthate. The violent rolling had breached its packaging. Seawater reached the chemical. And potassium amalxanthate, when it meets water, doesn't just react. It decomposes into hydrogen sulfide and carbon disulfide, gases that are simultaneously toxic and flammable. The container ignited. Within hours, the fire spread to adjacent containers. The crew attempted initial firefighting, but this wasn't a normal fire. This was a chemical fire fed by its own reaction, with the water being used to fight it. Every liter of water sprayed on the xanthate produced more flammable gas. Resolve Marine, a specialized salvage company, was contracted for emergency response. The Maersk Trader and Maersk Tender, ocean-going firefighting vessels, were dispatched. For 5 days they fought the fire. Not by dousing it, because water made it worse, but by cooling the surrounding containers to prevent further spread and letting the chemical reaction burn itself out. 5 days. On a ship carrying thousands of tons of cargo, anchored off one of Canada's most pristine coastlines. Who really failed? Here's the forensic question. Who failed? The captain. He followed protocol. He anchored where he was told to anchor. The crew? They fought the fire with the equipment they had. Samsung Heavy Industries? They built the ship to specification. The answer is, the system failed. The ZIM Kingston was fully SOLAS compliant. She passed every inspection. She met every requirement. But no regulation required a parametric rolling detection system. No rule mandated that crews be trained to recognize it. No protocol existed for what to do when your ship begins resonating with the ocean. The ship had an analog inclinometer, a device that tells you how much you're rolling, but it doesn't tell you why you're rolling, and it doesn't tell you that each roll is going to be worse than the last. The ZIM Kingston had every instrument the law required. She just didn't have the one instrument that mattered. And there's a second system failure, the port backlog. The ZIM Kingston was forced to wait at anchor, fully loaded in open water, during storm season, because Canadian ports couldn't process vessels fast enough. A ship designed to be in motion was forced to sit still. And a ship sitting still, beam on to incoming waves, is a ship waiting for parametric rolling to begin. The supply chain didn't just delay cargo, it created the conditions for a disaster. After the ZIM Kingston incident, the International Maritime Organization began reviewing whether active roll detection systems should become mandatory. Several shipping companies voluntarily installed real-time monitoring systems. But as of today, there is still no international requirement for parametric rolling warning systems on container ships. Every container ship in the world sails with the same blind spot the ZIM Kingston had. The ZIM Kingston incident left 109 containers in the Pacific Ocean. Debris washed ashore for months. Cleanup crews pulled refrigerators, tires, foam insulation, and shattered goods from beaches that had been pristine days before. The environmental cost has never been fully calculated. It probably never will be. In 2023, a research team at Memorial University in Newfoundland published a study on parametric rolling in container ships. Their conclusion: the current regulatory framework does not adequately address the risk of parametric rolling in large container vessels. The ocean didn't break the ZIM Kingston. Math did, and the regulations still haven't caught up. This is what system failure actually looks like. Not a villain, not a storm, not a mistake, just a gap between what we understand and what we require. If you want to understand how systems fail, not people, not machines, but the rules we write to keep them safe, subscribe. Because that gap is everywhere, and we're going to find it. This container ship lost 109 containers, and nobody understood why. Alt 1. This container ship was destroyed by a math equation. Alt 2. This container ship lost 109 containers in a storm nobody saw coming. In October 2021, the container ship ZIM Kingston lost 109 containers in the Pacific Ocean, and then caught fire for 5 days. But the cause wasn't a hurricane or a rogue wave. It was parametric rolling, a resonance phenomenon that no regulation required the ship to detect. This is a forensic breakdown of how a fully compliant, modern container ship was defeated by physics, and why every container ship in the world still carries the same blind spot. Transportation Safety Board of Canada, ZIM Kingston Marine Investigation Report. IMOMS, see Circulars on Parametric Rolling, MSC.1/Circ.1228. Memorial University, Newfoundland, Parametric Rolling Research, 2023. Scale Model Test Data, 1 to 50 ZID, IM Kingston Hull. Tags, ZIM Kingston, Container Ship Disaster, Parametric Rolling, Ship Loses Containers, Container Ship Fire, Cargo Ship Accident, Maritime Disaster, SOLAS, Shipping Disaster, Forensic Breakdown, Cargo Ship Storm, Container Ship Accident Pacific. Forensic Marker. Number 1. Port Backlog Forces, loaded vessel to hold beam on in open storm season waters, no contingency protocol. Forensic marker number 2, peak lateral acceleration, 0.95 g versus 0.6 g, lashing design limit. No parametric rolling detection required by law. Forensic marker number 3, 5-day chemical fire. Standard water suppression counterproductive. Accelerated the chemical reaction. Forensic marker number 4, fully SOLAS compliant. Zero mandatory parametric rolling detection or crew training requirements. Forensic marker number 5, 109 containers on Pacific seabed. Full environmental cost, unquantified. If you want to understand how systems fail, not people, not machines, but the rules we write to keep them safe, subscribe, because that gap is everywhere, and we're going to find it.